Good afternoon, ladies and gentlemen. My name is Ana Girao Coelho, and I'm going to give a presentation on the second generation of Eurocode 3, with an emphasis on parts 1.1 and 1.8 for general rules and the design of joints. First of all, let me tell you a bit about me. I've been involved in the development of European standards for the design and execution of steel structures for more than 20 years now. I'm currently a member of a CEN committee, TC250, which is the General Technical Committee for Eurocodes, and in particular Subcommittee 3, which is the subcommittee that looks after the evolution of Eurocode 3. I was also a member of the project team for the development of the second generation of Part 1.8, and I've been the chair of this working group for the past 4 years. Before starting the presentation, let me just say that if you have questions, please use the Q&A tab that you can see at the bottom of the screen, and you can ask any question as the webinar proceeds. I will try to answer all the questions at the end of the webinar. I'll now switch off my camera. I'll switch it on back at the end of the presentation. And moving on to the slides, I'll first give you an outlook of the contents of my presentation. So I'll start with a brief overview of the first and second generations of Eurocodes and their implementation. I'll then highlight, sorry, let me just start my pointer, right. I will then highlight some of the key revision aspects and focus on the specific changes for parts 1.1 and 1.8. I've included as well just a slide for the new part 1.14, which is for the design assisted by finite element analysis. I'll conclude by highlighting some of the next steps. So perhaps I should start by saying that the Eurocodes are documents that are essentially an agreed way for the design of building and civil engineering works. They capture the best practices across Europe and were developed through a process of consensus building among experts and other stakeholders. Now, consensus means an outcome that everyone can support, is not a majority decision. And this is quite important for us to be aware of. The first generation of Eurocodes was published between 2002 and 2007, following the conversion of the ENV standard. And it replaces all existing conflicting national standards to establish a set of common rules across Europe. In the UK, and for the design of steel structures in particular, it replaced the old BS 5950, which was finally withdrawn in 2010. The Eurocodes, so the first generation of Eurocodes, was reviewed under the European mandate M515, which set the strategic direction of the evolution of these standards and identified the main technical areas for improvement. So these are listed here in the first 4 bullet points. And 34 countries and more than 1,000 experts worked together in this project. It was a very lengthy project that has not finished yet. The main priorities of the mandate are also summarized in the second set of bullet points, and perhaps I would highlight the key priorities on ease of navigation or ease of use, and most importantly, the consistency within and between the Eurocodes. A good example for the ease of use, the improvement on the ease of use, was the introduction in various parts of the Eurocode of flowcharts, where possible, obviously. Another example of improvement of the ease of use is the clarification of the verbal forms used to express the requirements in the Eurocode. So there are 4 different verbs: shall, should, may, and can. And each one of them has a specific meaning within the Eurocode context. Shall is used for principles. So for example, a structure shall be in equilibrium. The verb should is a very strong recommendation to follow a specific requirement. May means permissibility, and can a capability, a possibility. So you have to be aware when using the code which type of verb expresses a specific requirement to understand whether you can or cannot deviate from the rule. These next slides explain the structure of the various Eurocodes. So at the moment, we have 10 codes, soon will become 11. As part of the mandate, there would be the development of a new Eurocode for the design of structural glass. And each of these standards are further subdivided into a number of parts. The first generation comprised in total 58 documents, and this number has now increased to 65 in the second generation. Each Eurocode is also accompanied by a national annex, and we will talk about that in the next slide. You have 2 material independent Eurocodes, Eurocode 0, which is for basis of structural design, and it gives the principles and requirements for safety, serviceability, robustness, and durability of structures, and these are common to all Eurocode parts. Eurocode 1 specifies the actions that you need to consider in the design of structures. Then this diagram shows the 6, again, soon 7, material-specific codes. And you have for concrete, Eurocode 2, Eurocode 3 for steel, 5 for timber, etc. And there are 2 additional Eurocodes, 7 for geotechnical works and 8 for seismic design. The national annexes are key documents, and they accompany the Eurocodes to allow, in a way, that each Eurocode is set at the national level through national choices and decisions for a project in a specific country. And they include the nationally determined parameters, the NDPs, which include, for example, the partial factors that you should use in design, some country-specific data, as for example, wind maps. On the right, you can see the current wind map for the UK, or for example, the seismic map zones of a specific country. I show here the case of Portugal, which divides the country in different seismic areas. The second generation of the national annexes will also allow the references to non-contradicting complementary information, the so-called NCCI, to be directly included in the national annexes, and this will be very useful. Essentially, these NCCIs, you can understand them as clarification to the requirements given in the main body of the code. Now, what the national annex cannot do is to modify or cancel content of the Eurocode part itself. So it just gives the country-specific application scope, let's say. And effectively, it set the levels of safety and reliability in a specific country. Focusing now on Eurocode 3, these next two slides show how this Eurocode is organized. There are 7 application parts which are structural specific. So for example, you have part 2 for bridges, part 5 for piling, etc. Part 1 is the main document, and it gives the general rules and rules for buildings. And then it is further subdivided in 14 parts, which we'll have a look at. Just to note something, in brackets after each part, you have here what I call the DOP. DOP stands for date of publication. And you can see that there are, for example, in terms of part 1, there are already several parts that have been published. So 1.1 through 1.5 have all been published. And then in this slide, you can see 1.6 to 1.10, the same. And part 1.13, which is a new part for design of beams with large web openings. It has also been published by the BSI. This year, it was the end, part 1.14, which again is a new part for design assisted by finite element analysis. This should be available later this year as well. This slide explains how the Eurocode 3 is implemented. So it is a part of a family of standards for the steel construction sector. And the Eurocode is the design standard, but it should be used in combination with other standards that have set out specific requirements for production, for products and execution, so fabrication and erection, as well as sustainability. I'll give you a simple example that illustrates this key partnership between the different types of standards. When you design a steel column for buckling, you obviously make assumptions for any possible lack of straightness of that column. And therefore, you will need the product for manufacture, but as well as the execution for the erection of the column to make sure that those tolerances are not exceeded. And as I've said, you will also need the national annex for any of the specific parts. This slide summarizes the key revision aspects for the second generation. In the revised standards, so the rules for steel grades up to S700 have been incorporated into the various parts and subparts of Eurocode 3. Now, remember that in the current first generation, the limit was S460, and then you would have part 112 that would give additional rules for steel grades up to S700. There is a new part which is still under development, a new part 112 for the second generation, which will now give additional rules for steel grades up to S960, so a yield strength of 960 megapascal. The table of contents have also been revised to follow a common set of headings, and we'll see that in the next slide for part 1.1 in particular. And there was also an effort to reduce the number of NDPs, so the nationally determined parameters, and also the number of alternative rules for the same requirements in terms of design and within the same part of the Eurocode. Now, the Eurocode standards, not only Eurocode 3, but all Eurocode parts in general, will follow the same sequence to make it easier for designers to locate the same design information in each of the different standards. In this table, we compare the current table of contents with the table of contents in the second generation. So you can see now that the current section 1 general has been split into 3 different sections. So scope, normative references, and terms, definitions, and symbols. A downside of this change, obviously, is that most clauses and equation numbers will have changed, and designers will obviously have to relearn where things are and the clauses that need to be referred to in the design calculations. As I said, I'm going to compare here the various contents on part 1.1, and I'll focus first on the sections that have been withdrawn, which are strike through. So Annex A in the existing code has the coefficients for the interaction formulae for combined axial and moment, and now has been moved into the new technical specification, which is for alternative interaction method for members in bending and compression. Annex B, which was for an alternative method, it also gives these coefficients for the same interaction formulae, but it's much simpler than Annex A. And this simpler approach has now been moved into the main text. You can find them in the new section 8. Annex AB1, which had only a few paragraphs about nonlinear analysis, has also been moved into the main text of the code. Annex BB1, which was about buckling in triangulated structures, and it gave effective lengths and slenderness of diagonals in a truss, and it has been moved into a technical report. So the information is still available, but in a separate document. Annex BB2 was about continuous restraint, such as if you have a compression flange restrained by sheeting, and it has now been moved into the Annex D in the second generation. The values for the coefficients K theta have been modified, and this annex is now a normative one. Previously, this was informative information, informative guidance only. In terms of withdrawn sections, Annex AB2 was a small section telling you how to calculate the bending moment in continuous floor beams. In the existing document, it actually says that this information would be at some point moved into Eurocode 1, as this is a loading issue. And now you can find that information in this second generation of Eurocode 1. Annex BB3 is the one that has the stable lengths of segments containing plastic hinges for out-of-plane buckling. This was the content that was brought from BS 5950, obviously rewritten in Eurocode language, and it has been removed entirely from the scope of Eurocode 3 Part 1.1, because this has always been seen as a UK-specific issue. We will make, however, these requirements available in the revised SCI publication P399 for portal frames, and we'll make a reference to this revised publication in the UK National Annex, so you can continue using the guidance. We'll now have a look at some of the specific changes in Eurocode 3 Part 1.1. There are many changes, and I'm not showing all of them in these slides. I'll try to summarize what I think are the most important changes for most designers. However, I should note that in each of the new parts of the Eurocodes, you have in the European forward a list of the main changes in each part. So for example, in part 1.1, there are 10 main changes listed, and you can see them already in the BSI publication. So we start with structural analysis, which is now given in section 7. The declared intentions of the project team members for the revision of this section have been published in an article which is available, and I think you find it useful. I give here the link to that document, which is available for free download. And when you receive the slides, you can have a look and go through the contents of this paper. So the authors tell you that they largely retain the same content that exists in the current section 5, but try to clarify such content to avoid misunderstandings. And in all countries, I think you will continue implementing the structural analysis as you are used to. The rewriting has been quite helpful, and they summarize the various methods for structural analysis in this flowchart. However, they labeled it slightly differently, M0 through M5, and there is also this alternative method here that we'll look at later. I've also added next to each of the methods some comments that you might find useful. So let's look first at the first pair, M0 and M1. So these are for stocky members in both cases. And you can see that they are for an alpha-cret non-sway greater than or equal to K0, with a recommended value of 25, given this paragraph 4 of section 721. This is an NDP, however, and it's equivalent to considering a plateau of a lambda bar of 0.2. This is the first question box you have here. There's also a value here for alpha-cret sway that should be greater than or equal to 10 for application of these two methods. And in this case, you won't need to consider any buckling effects. There may be lateral torsional buckling, and paragraph 6 in 721 tells you when you may neglect these effects. In practice, with these values of alpha-cret, it is unlikely to have lateral torsional buckling. So M0 and M1 are the sort of structures that you are unlikely to have to design. If we look here now at the last column in this table, you can see that for some of the methods, a first order analysis is possible. So the first 3 methods, M0 to M2, allow you that. And for others, you will need to carry out a second order analysis of the structures. That's for M3 through M5. I'll have a look at the alternative method later. So the next method to look at is M2. This is for an alpha-cret sway greater than 10 and applies to cases where the frame is prevented from sway, say by bracing or a lift shaft. You'll be carrying out a first order analysis, and there will be a significant number of frames that you will analyze using M3. It's already a common, M2, sorry. And then you will have to carry out the checks that you would expect. So column buckling, lateral torsional buckling of columns and beams, and the sway effects defined in the code as sway forces. This will be applied to the lift shaft or the stiff brace bay, whichever it is. The last set of methods, M3 to M5, should be done by second order analysis. In method M3, you can see here in the comment box that the second order analysis is sufficiently accurate, even if it's amplified first order sway moments added to the first order analysis. This will be applicable, you can see here in the other question box, to buildings where the columns are not very slender, and this is assumed to be for an axial load not greater than n-cret over 4. So now note that this is not the same as alpha-cret. Alpha-cret is for the whole structure, whereas n-cret is for a compressed member that is considered to be pin-ended. If you now look at paragraphs 11 and 12 in section 722, which are very similar to the corresponding clauses in section 5 in the current part 1.1, it is saying that if you have an alpha-cret sway of 3 or greater, and if the failure mode is broadly similar to the first elastic buckling mode of the structure, then you can just use amplified first order sway moments, and that should be sufficiently accurate to assess the second order effects on the structure. Method 4. This is for analyzing structures that are more slender than those allowed in M3. In this case, the sway buckling will be significant. Columns are slender, so you will have to apply both sway and member imperfections. The member imperfections can be applied as shape of the member, or perhaps more conveniently as applied loads along the member with obviously the corresponding reactions at each end. You will have to check column buckling and lateral torsional buckling, but when you check the MN, so bending and axial load interaction, you'll only need to satisfy the second equation from the pair of equations for the interaction, which is the one that only considers minor axis buckling of the column in addition to the bending moments. Lastly, M5 requires you to consider all the imperfections defined in the code. You'll only do cross-section checks, and these are limited to linear interaction, considering axial force and bending in both directions. You shouldn't expect method M5 to be very common in practice. So the problems in methods M4 and M5 for a designer is that it's often difficult to know which direction to put the member imperfections will give the more onerous result. So member imperfections might be considered in a direction that strengthens the member rather than weakening it. I hope I explained the flow chart in sufficient detail. I think this is certainly helpful, at least for new designers. I'm not going to spend a lot of time on this alternative method, EM. It's basically the equivalent member method that we used to do with BS 5950 and its annex. I should say that this is also an NDP, and the current draft for the UK national annex stipulates that this should not be used. So I'm not going to spend much time describing this method. Another change was the revision of the classification of cross sections. And here I would just like to note this following aspect. So there are more severe limits on the width to thickness ratios for internal compression parts, such as the web of a beam or a column or the wall of a box column. And this means that some section may become a higher class. This is the outcome of research from about, I would say 10 years ago on plated structures. And they found out that the current guidance sometimes was unsafe, and therefore you have different limits now. Outstand flanges remain the same. Bending of circular hollow sections now has a more generous slenderness for the walls for class 3 sections, because in bending part of the cross section, part is in tension, and therefore the whole section is more stable than if it's under compression only. Elliptical hollow sections have also been added. Just as a final remark, I would like to note, and I think we will look at that in a next slide, there are new rules for semi-compact sections, and these can now be found in the new Annex P. And it often will mean that the resistance of a class 3 section will be based on effective plastic properties, which can be very close to the plastic resistance. And this was already included in BS 5950, and obviously will lead to more economic designs. So essentially what they do is in bending, they consider an effective section that is considered by a simple interpolation between the plastic and elastic section modulus using width to thickness ratio values for that particular section. Now we come to lateral torsional buckling, and the changes to some formulae in the new section 8.3 are probably the most significant in the code. There has been a lot of research work on lateral torsional buckling resistance using finite element analysis, assuming nonlinear material, geometric nonlinearities, residual stresses. And the outcome of this research is that there is evidence that obviously different section shapes will have different lateral torsional buckling curves. So if you have a UB with a wide flange, it will have a slightly different buckling curve to the same UB section with the same depth, but a narrow flange. And the researchers, they actually believe that a more accurate lateral torsional buckling resistance can be now calculated, and therefore they have changes the LTB equations in the code. So in this slide, again, I compare what's now in the current code and in the second generation for part 1.1. We have currently three different sections on your left, on the left of the table. So you have a general case, rolled sections, and then a simplified method. What is now being proposed is, again, a general case. The case for doubly symmetric I and H sections, and again, a simplified method. So in the current part, the general code works off a plateau length of 0.2 that you can see here in the phi T equation. There's a very similar equation in the revised code that can be applied to all sections, and it shows in particular how this applies to monosymmetric cases as well. The next case is for rolled sections or equivalent welded sections, although the UK National Annex only uses it for rolled sections, not welded sections. And this was because the available test data was compared. So at the time, the first generation of the National Annex was developed. And the comparison of the available test data with predictions of the resistance by using the gamma M1 equal to 1 and it was concluded that only the rolled sections would satisfy the reliability requirements, and therefore the UK National Annex considers welded sections as part of the general case. So you can see here that there is this hill plateau of lambda bar LT naught, which the National Annex adopted as 0.4. What is now being proposed in the new code in section 8323 in paragraph 3 for rolled sections is that the plateau length of this curve is now fixed at 0.2. The revised simplified method is also identical to the current formulation, but you'll see that there are some changes in the factor lambda F that you use. So this is the equivalent compression flange slenderness. In the next slide, I will focus mainly on the case for rolled sections, which is rather common. So table 8.5, which is taken from the second generation of part 1.1, it shows the imperfection factors for lateral torsional buckling of doubly symmetric and I and H sections. The last column, you can see that the imperfection factor alpha LT is no longer a single value. For example, if you look here for the first case, for example, you can see that alpha LT is given by 0.12 multiplied by the square root of the ratio between the elastic moduli of the section with a limit of 0.34, which is the value we currently have. There are also different expressions to compute chi-LT and phi-LT in the current code. They bring in a moment gradient term Fm, you can see in both equations, which is defined as a factor that accounts for the effect of the bending moment distribution between discrete lateral restraints. The code tells you that you can conservatively take this factor as 1 in cases that cannot be approximated by the diagrams that are given in table 8.6. I'm not showing that here, but you can see more favorable values for FM in case you know the shape of the moment diagram curve and if it fits in this table 8.6. You should also note that now in this bracket here, it appears lambda bar Z, not lambda bar LT as before. So you have to be careful with the values that you input. As a general comment, I would say that you will be expecting lower resistance for lateral torsional buckling compared with the current provision. So depending on the cross section, the new resistances can be of the order of 85% of the current predictions, which is quite significant. The last thing to look at is the interaction between compression and bending. So the equations remain the same as we have at the moment in section 6, but now we use these coefficients K as given from current Annex B. Moving on to new sections. In the second generation of part 1.1, you have these 7 new sections, which you can read. I'll just briefly go through the ones that are noted in bold font. So in section 8314, you now have requirements in cases you have torsional buckling and torsional flexural buckling of doubly symmetric sections. It gives you modified curves. It gives you different imperfection factor alpha TF. So you'll need to implement this in your spreadsheets or the software you use. If you have buckling of monosymmetric sections with compression and bending, the existing code doesn't tell you exactly what to do. This information is now given in Annex C1, and there are some modified K YY values, but the application, I believe it's quite straightforward. The final section I would like to talk about is this new Annex E, which basically contains a list of statistics that are assumed in design formulae in the code. This is not intended for designers to use. This is just an informative annex and will continue as an informative annex in the national annex. This annex is mainly for steel producers to let them know what the code writers expect them to produce. It is expected that this annex will be moved into the product standards where actually it belongs to. From a UK perspective, I should note that, and in terms of development of the national annexes, we have been through the statistics and they are very much the same to those used in deriving the partial factors that are adopted in the UK for the first generation of Eurocode. So there's nothing to worry about in terms of the production for the steels that are currently used in the UK. So I move on now to part 1.1.8 for the design of joints. As for part 1.1, the table of contents has been revised to follow the first 4 common sections, and therefore the section numbers to the following sections are all increased by a factor of 2, obviously. There are 4 new annexes, but their content is not really new, other than Annex C for simple joints. The current code in section 6, which is very extensive, the content has been mostly moved into Annex A, B, and D. I can say that unlike part 1.1, in which there was some removal of content for separate documents, that didn't happen for part 1.8. So very briefly, I know I have 13 slides on the specific changes, but I won't spend much time. I would just like to note the main changes in this part 1.8. Just to say that the European forward in the second generation for part 1.8 lists 12 main changes, and I'll address some of these. So in basis of design, there is now a new provision that allows you to characterize the structural properties of joints by finite element methods. So in line with the new part 1.14. As I said, I'll talk about that later in one of the last slides. One significant change in the second generation of part 1.8 is the calculation of the bearing resistance, and this has significantly increased now. And the new formulae was based on extensive research that was carried out by a team at the University of Ljubljana in Slovenia. So the current formulation depends on the position of bolts. So in terms of end and edge distances, E1 and E2, and spacing in both directions, P1 and P2. If these distances are large enough, then you can approximate the bearing resistance by this formula given here. So you can note the factor 2.5. In the second generation, the edge distance E2 and the gauge distance P2 are no longer used, as you can see here in these expressions. There's also a new KM factor that depends on the steel grade. Please bear in mind that the scope now has been extended to S700. And for mild steels, and again, if the distances are large enough, the equivalent bearing resistance is now given by a factor of 3 times that ratio. And this is quite significant because there is an increase by 20%. I would also like to draw your attention to this requirement here. So as you know, bearing design is more concerned with avoiding excessive old deformations than with avoiding actual failure of the connection. And the code recognizes this and therefore gives a limitation to the bearing resistance in these cases by bringing in this factor alpha B red for reduced. And this is given in paragraph 3 of 591. So this paragraph explains how to compute this reduction factor, which again depends on the steel grade. This reduction factor can be obtained from A522, which is for the component bolts in bearing, and it proposes as a default a limitation of deformations to bolt diameter over 6. So this coefficient alpha B is given in the previous table I've shown. Another change to note is for the design resistance of a group of fasteners, as for example in this connection showed here in this picture. Currently, there is a very simple requirement in this clause 3.7 that depends on the so you will compute the design of a group of fasteners depending on the relative magnitude of the shear and bending resistances. In the second generation, we've introduced some ductility conditions. Again, don't forget that we've extended now to S700. And the resistance of a group of fasteners will depend on whether that criteria is satisfied or not. So a bit of more complexity in these revised clauses. Another change in section 5 is for the design of pins. So currently the code allows you to design a pin connection as a single bolted connection if you satisfy certain requirements. This is given here. There was some research work in this area, and it showed that this is potentially unsafe, and therefore this possibility is no longer in the code. Moving on to section 6 for welded joints. So the current code assumes that the filler metal, so the weld metal, has identical or better properties than the parent metal. So you're looking at matching or overmatching electrodes. Because we now deal with higher strength steel grades, the possibility of using undermatching welds is also allowed. There are alternative methods that specifically account for the filler metal properties. So in the case of higher strength steels, and these formula are given as alternative expressions for evaluation of the design resistance of fillet welds for the two optional methods, and also for full penetration butt welds. So in the next slide, I'll show the two possibilities for the design of a fillet weld. So the general case in the second generation, so this equation 6.1 is well known. It has not been modified in the current code, from the current code. The correlation factor beta W now has also been derived for steel grades S450 and obviously steel grades above S460. Note here in the last column, I show two values. These have been modified for S420 and S460. Currently it's 1. Just found that you could work with a lower value for beta W. These modifications are supported by research carried out at University of Stuttgart. As an alternative, and in the case of steel grades higher than S460, you now have an alternative equation in which you consider both the ultimate resistance of the parent metal and also the filler metal. And it gives you, in the denominator here, coefficient beta W modified that now depends on the filler material, not the steel grade of the plates as the original correlation factor. No major changes in clause 7 for structural analysis. I would just like to note some modification of the classification boundaries for stiffness, although this is not widely used in the UK. So as you know, you have 3 zones: rigid, nominally pinned, and in between the so-called semi-rigid. These boundaries obviously depend on the relative stiffness of the joint and the members that are connected. The limit zone for nominally pinned connections, which is in the current code, has always been questioned by experts. So now we simply say that nominally pinned connections can be those in Annex C. Another relevant modification in the second generation relates to the component designation. The list of components is now given in table 8.1, but all individual properties, so resistance and stiffness coefficient, are now given in a separate annex. It's the new Annex A. The components are no longer referenced by a number. They are referenced by an abbreviation in which you see that C, other than column, also refers to compression, T for tension, and V is for shear. P obviously is plate, F flange, etc. We believe that this new designation is a better reference than the previous numbering system. There are no significant changes in the evaluation of the characteristics of most components, although I would note that the formulae for evaluation of the design resistance of a web panel in shear, so WP, has been reviewed in line with recent research carried out in the University of Liège. And there is also, as I already mentioned, a more sophisticated model for the full evaluation of the force deformation behavior of the component bearing at bolt holes. 2 new components, these are noted here as well. So in line with the new part 4 of Eurocode 2, which deals with the design of fastenings for use in concrete, the code has now added 2 new components: the fasteners between steel and concrete in tension and in shear. Let me just say that this detail of base plates is not commonly used in the UK, and these components will be only referred to in design of column bases in Annex D4. This is a complete separate section from the design of column bases with anchor plates, anchor bolts, which is Annex D3. The requirements are completely separated, so I don't think you will find any significant differences to what you are used to do. The next change I would like to highlight refers to the evaluation of rotation capacity of joints. As you know, the code does not give you a procedure for direct evaluation of the rotation capacity of a joint, but gives some indirect guidance by using resistance. This current clause, 6413, stipulates that you should have sufficient rotation capacity for a joint as long as the joint design resistance is at least 20% higher than that of the connected member. So the corresponding paragraph in the second generation makes this overstrength dependent on the steel grade. You can see this here in table B4. So for the common use grade, the S355, we are now looking at an increase of 25%, so just a bit of a higher requirement. Finally, clause 9 for hollow section joints has been completely reviewed in terms of presentation only. So the expressions are largely the same, but the design tables have been reviewed for clarity. I actually think that the revised design tables read much better and give more complete information regarding all the design checks that you need to carry out. Also, and this is change, the provisions for the design of welds in hollow section joints have been clarified, and you need to ensure, in line with this paragraph 2, that you design full strength welds, that is, a weld designed to transmit the design resistance of the weaker of the parts joint. Only one new section in Part 1.8, as I've already said, Annex D, for the design of nominally pinned connections. The guidance given in this annex follows the European design recommendations that have been published as an ECCS guide. The UK will likely continue using the Green Book as there is an NDP in Annex C that allows countries to give alternative rules to Annex C. In this annex, you have 3 different sets of checks. If the joints satisfy the ductility and rotation capacity requirements, which are relevant, obviously, for nominally pinned joints, evaluation of design resistance of the joint, and the tying resistance to satisfy the robustness requirements. The last part of the second generation of Eurocode 3 that I would like to briefly mention is the new part 114 for design assisted by finite element analysis. So this is an entirely new part and would require a webinar on its own. This standard has been circulated for formal vote of the countries. Paraphrasing the scope of the standard, so Eurocode 3 Part 114 gives requirements for use of numerical methods in the design of steel structures, including ultimate limit states, fatigue, and serviceability limit states. It also gives requirements for the application of advanced finite elements and similar modeling techniques, which can also be used in design. The good news about this new part is that it will be published with a companion technical report, which gives background information and explanations to the design rules. And it gives a series of validation and design examples in line with Part 114. So in the diagrams on the right, these are snippets from the technical report and are for an example of flexural torsional buckling of a cold formed steel column. In this particular example, as many others, you will have included an assessment of the imperfections, the steps towards model verification, and also validation. In this part, you'll find guidance on the various aspects of modeling as well, analysis and verification of the finite element model, a design methodology when checking ultimate limit states, fatigue and serviceability limit states, as I said. And the last section is quite important. It gives requirements on the relevant documents that you need to include. And you will see that this is an extensive list of data. As a final remark, Part 1.8, as I said, it now allows you to design joints by finite element analysis, but it will soon include a new annex that we are currently developing, and this will give additional guidance for design of joints by finite element analysis. Just to conclude, and I understand I've reached the end of the webinar. So I would just summarize what I believe are the next steps before the second generation of Eurocodes, before they come into force. Please note that at the moment, the UK National Forward clearly says that the first generation of documents are the applicable standards, and this is until 30th of March 2028. It also notes that you should only use the second generation in conjunction with the national annex, and these are still under development. And the BCSA is actively engaged in the development of the Eurocodes. In addition to being involved with the Steelwork, we are also supporting the development of the national annexes, and also the revision of the Eurocode design guides. The current editions are available in steelconstruction.info. We are also giving webinars such as this one and developing educational material to make sure that the industry is ready for the introduction of the revised standards. So this ends my presentation. I hope you found it useful, and I'm now available for any questions or comments.
Thank you very much for that, Anna. It was extremely informative. We've had one question so far, which was to do with the technical reports and where they can be found.
I'm assuming that it's this technical report for part 114. It hasn't been published yet. I assume it will be published together with part 114. So it should be available towards the end of this year, 2025.
That's all the questions that we have, unless anybody else wants to ask a question now. No, well, thank you all for attending. We will put, oh, we have got one. Where will it be available?
You can download it from BSI website, BS online.
Thank you very much. Well, thank you all for attending. We will make this webinar available on our BCSA YouTube channel, and we will also distribute the slides afterwards. Thank you once again, Anna. Really appreciate it.
Thank you for your support, Zari. Bye.